the container of the land and the waters from where we're coming today. The Wurundjeri people of the Kulin Nation, I pay my respect to their elders, past, present, and emerging, and embrace their continued connection to this place. I pay my respects to all other Aboriginal and Torres Strait Islanders who may be joining us today. This always was and always will be the Aboriginal land. And a little bit about Our Ladies. We're a registered non-for-profit organisation and a local chapter of Our Ladies Group, which aims to promote gender diversity in our community in both Australia and worldwide. And today we'll have Sherry presenting the spatial-temporal analysis with cubble. And our next event is going to be how I use workflow art to create reproducible analysis. So stay tuned and save the date on the 30th of October. I will be held as Soviet, and the presenter is Giovanna Maximovic from Peter McCollum's Cancer Center. And if you want to support Our Ladies, you can find us on Twitter. And we're also looking for volunteers to help us to set up the event. So today we actually have 2 new volunteers today joining us. They're here. Thank you so much. And then if you wanted to give a talk, please contact us. You can find us on Twitter, GitHub, Meetup, YouTube, LinkedIn, and Facebook. And welcome, Sherry. So Sherry is a PhD student at Department of Econometrics and Business Stats at Monash. She's also the main organizer for NUMBATs event at Monash. Okay. Her study is focused on spatial-temporal data analysis. Thanks, Sherry.
Okay, I do the share first. Okay. And does people online can hear me all right? Okay, cool. So thanks Our Lady Melbourne for inviting me for this talk. So the title of my talk today is switching between space and time, spatial-temporal analysis with kabble. So this is a little bit about me. I'm currently a third-year PhD student in the Department of Econometrics and Business Statistics at Monash University. And my research centers on exploring multivariate spatial-temporal data with data wrangling and visualization tool. So here I give you an overview of my talk today. So after some introduction, I will first talking about spatial data with the SF package, and then the temporal data with the tsibble package, before we move into spatial temporal data with kabble. So in kabble, we were talking about data wrangling in space and time. And finally, we will do some visualization with glyph map. So if you want to follow along the slides link is available here. So Ada, would you be able to share that on the link? So if people get a computer and would like to follow that, that would be great. And once you get the slides link, you can click onto here to see the slides report. And there's an index.r file where you can try out actually all the codes by yourself. So about spatial temporal data. So data with different spatial and temporal characteristics can all sit under the big umbrella of spatial temporal data. So here I give you 3 examples, the vector data, raster data, and trajectory. With vector data, we have time series that measured at a collection of locations. So here we have an Australian map, and then there are dots, there are weather stations that's measured there. With raster data, it uses gridded cells to represent a continuous space. And then each cell has variables that measured at different time points. So you can think of it as you are taking screenshots or snapshots of space at various time point, and you stack them on top of each other to form a spatial temporal data. And lastly, trajectory data, on the other hand, it has points that's moving around on the space-time caveat. So here, each point on those wiggly lines, they would have a different longitude, latitude, and time markers. So it's moving on the space-time caveat. So these are three different representations of spatial temporal data, and they all have their own their own wrangling and visualization tools, and some of them are not are not neutral. So that's why I always feel like people can talk about a whole range of different things when they say their data are spatial temporal. So the talk of today, we will be focusing on the vector data, the simplest case. A major source of vector spatial temporal data is the physical sensors. They can be used to measure a wide range of climate variables. For example, there's temperature sensors, rainfall sensors, wind speed, wind director gauges, and also water level sensors. So with those data, typically what you get is a spatial data, which you can choose a list of stations that you're interested, and then you will be able to queue the temporal data from their spatial list. So in the end, what you will get is a spatial data sheet and then a temporal data sheet. So what we'll do today is we will first talk about the spatial component of this type of data, and then moving to the temporal side of it. So there are two ways where you could represent spatial temporal data in R. So the first way is to use two separate longitude and latitude column, like in here. And then another way you can do is to use the simple feature representation with the SF package. So what I show here are the same data, but in the first representation, you have the ID and longitude, latitude for the location, the elevation for the altitude, and then there's a station name and there's a WMO ID. So that's the World Meteorology Organization ID. So some station would have it, some station would not. And then it's the same data that's being loaded loaded as an SF object. There's a little bit heading that's going on here. It shows you there's 30 features, there's 30 observations corresponding to 30 rows here. And then there's 4 rows. The geometry type, the bounding box, the CRS, we will dissect that a little bit later, but these are the header information that the SF prints out for you. And then similar here, we have very similar things, but the longitude and latitude is wrapped up in this geometry column. The benefit of using the relatively complex SF representation is that it also gives you access to many geometrical operations. So here I have a few examples I sketch out for you. So SF buffer would allow you to add a little bit buffer area around your points, around your lines, around your polygons. STcast allows you to cast a line string or one geometry type to another. So here I have cast from a line string to points. STcentroid allows you to calculate the centroid point of a polygon, and then there's STcoordinates, which allows you to extract coordinates from a geometry type that you give it. So we will revisit this sketch a little bit later. So I will then talk about a few confusing or interesting pairs, but for now there's also more than just the ones that I have here. But the purpose of this slide here is mainly to illustrate you get access to a lot of geometrical operations if you use the SF representation. It's already this inbuilt function that allows you to do these operations. Also with the SF object, you can directly do the plot with the SF geom SF. So you only have to supply an SF object into the data, and it will automatically decompose the geometry column for you and make it onto the plot. So here on the left, I have the shape of the Australian border, and then the stations I'm interested. On the right here, there's a few other options that you can do with SF. There's SF geom SF label that allows you to add the label rather than just doing the points on your plot. And you can also customize the aesthetics and then add theme onto your ggplot map. So there's other functionalities within the community that allows you to plot with plot maps with ggplot objects. So for beginners, the SF header and all its prints can be a little bit difficult to work with. Here I'm showing you 3 different prints that you might just see quite often if you play around with an SF object. They may seem confusing as in how you would be able to perform operations on those objects. But especially with the SFC column and SFC geometry, because the print of it might not be familiar to you in the first go, that it's not one of like the basic data types that you are familiar with. But what I'm going to do next for you is to tell you that what actually underneath these prints are the objects that you have already familiar with. So underneath all those prints, the SFC, SFG, and SF, there are actually lists, double, and matrices that you have already seen. So let's do that. So first we will start with a simple feature geometry. So this is what you would see if you just print out one. And if you look at the type of it, I will tell us it's a double. And then looking at the attribute of it, we will see it has a class attribute. And then there are 3 classes that are associated with this simple feature geometry. And with N class, we would be able to remove the attribute and look at what's the actual things that's being stored. And what's actually being stored is a vector. It's a paired vector of longitude and latitude. So that's why I wrote at the front, the point SFG is a paired vector with a special class labels. And this particular representation or the format here is called the well-known text, which is a human readable encoding that the SF package use. So it's specialized written in this particular format so that it makes it much easier to read for much complicated geometry type that we will see just shortly. And building on top of the SFG, we have the SFC, which you would be able to see has a print like here. So it will show up all the headers that you probably has already seen, and then will shows the SFGs like here. You could also look at the type of it. Now you get is a list. And you look at the attributes of that, there's a few more attributes that's associated with the simple feature column. So there are precision, there are B-box, there are CRS, and there's an empties. So it has more than just the class attributes. It also has a few other things that will actually print it out on the header. And if we unclass it, what you will get is your 2 objects, and the 2 objects are just the SFGs that we just saw before. So what I have here is that the SFC is a list of SFG with special attributes. So in a sense, it is a list, and you will have the SFG that's inside of it, sitting inside the list. And building on top of the SFG and SFC concept, we have more than just the point as the geometry type. There are other geometry types, and I will introduce 3 common ones for you. The first one is a line string. So rather than just having points and then 2 numbers here, in the line string representation, you have a line string and then a bunch of numbers. So the type of it shows it's also a double. And then it's actually being structured as a matrix. So it's a matrix of paired doubles or paired vectors, and they are ordered in there's a particular order that if you're trying to link those points together, that become a line string. So there's more subtleties regarding to the order of it. You can't have some from the first point to the third point and then moving to the second point. It has to be ordered in this particular way so that they can connect it into a line string so that it's valid. And then we have polygons. So polygon is a little bit more complicated than points in line strings. So if you are really careful here, you will be able to see this. There's the double bracket here. So that's the subtle indicator that actually it is a list. And then what's slightly different from previous is that it's a matrix that's in a list. So look at previously, we have a matrix here. But the next slides, we have this little one in the double bracket here. It shows actually it's a list. So you can have a list with multiple matrices. So what I wrote here is that the polygon SFG is a list where each element in this list is a matrix of paired vectors. And then lastly, we have multi-polygons. So this is the most complicated one, but also the most common one you probably would see if you really work with spatial temporal data. So now here we have 3 little brackets. And the subtlety here is that rather than having a simple list, you will have a nested list. And in each list, it can contain multiple matrices of paired vectors. So it's simple, it's just you have another layer that's on top of the polygons so that you could include multiple matrices. So the benefit of that is if you look at Victoria's data, there's the Phillip Islands, that's a separate polygons from the main Victoria. So that allows you to store that in a single row. So that's a multi-polygon rather than a single polygon. So that's the difference about that. So a little bit summary about here. So the SF, SFC, and SFG objects, they have informative header prints that tells you all these things about what's the geometry type, what's the bounding blocks, what's the coordinate reference system. But what they really can be boiled down to the basic data structures that we are already familiar with. And there are more than just the geometry types that I introduced, the points, the line string, the polygon, the multi-polygons. There are a few others. There are multi-points, multi-line string, and there are also less well-known geometry types that's available from the SF package. And the good news here is that in practice, you actually don't have to decompose or manipulate those vectors or those matrices manually by yourself. The SF functions, the geometry operation, the ST functions that I showed you just before, they would be able to decompose that with the C++ function that help you to run all those functions, run the things you want to do really fast. And then there's visualization tools, the geom SF. Geom SF label allows you to directly supply an SF object into that function so that it will decompose the geometry column for you. So you don't actually have to extract the longitude, latitude, and play around with that and make sure it's former geometry, all those nitty-gritty things. Now, so what I want to do here again is to emphasize a few pairs that's really get me confusing in the first time. So I think it will be worthwhile to share with everyone to know about. So the first pair here is the ST combine and ST union. They take very similar inputs. So here I have 2 polygons. ST combine is a cheaper operation. What it will do is it will simply concatenate the object you supply to it. So once you have 2 polygons, you can concatenate them together. So it becomes a multi-polygon. But on the other hand, ST union is much more expensive in the sense that it will resolve the boundary issues and make sure things so these two polygons, they're actually next to each other. When they combine together, they can become a single polygon. So the ST union will do that boundary resolving issue for you. And what you will get out of it is just a single polygon. So if you have a really large data or like a moderate size, you want to be a little bit cautious when you're trying to do ST union, as sometimes it's computationally a bit intensive and it will take quite some time for things to render. And there's a few times where I can't wait enough and then I just hit quick and then it shut up. Yeah, it shut my RStudio and then I learned it hard way. So it may be worthwhile to know that ahead of time. Also, the next pair that's get me confusing, and I'm still confusing, is about the ST intersects and ST intersections. For me, they look too similar, and I never know which one to use at which time. So mainly ST intersects is a predicate function, which return the true false value about the geometrical position about two objects. So here I have point A and point B that's intersecting with the polygon. So it will return two truths. And then the C point is outside that polygon, so it does not intersect. So it will return a false. So in this sense, it's a predicate function. And then there's a few other predicate function that's within the SF family that allows you to do different relationships. For example, like within, touch, cover, cover by, all those. While on the other hand, the ST intersection, it will actually find the intersecting area and then return that as a polygon. So from the two polygons I have here, there's the common area in the middle, and then ST intersection will find this common area and return that as a polygon for you. So they're actually doing very different things, even though their names are too similar. And lastly, here I have the ST transform and ST is long-let pair. So these two pairs are related to the coordinate reference system of your data. Now, I think ST is long-let is easier to explain, so I will start with that. The first point that you see here, point 140, -34, you might recognize it's the coordinates for Melbourne, and it's measured in longitude and latitude. So it's actually a measure of angular on the 3D globe. So you have the globe here, and then there's longitude amount, which you move an angle, and then the latitude amount where you move another angle. So the unit of this measure is angle. Well, on this next point here, so it's a longitude latitude measure. So the function will return a true value. And then the next part here, the point, this long string positive and negative thing here, this is a projection of the previous point on the world Mercator projection. So what actually it do is that it's measured in meter in the 2D sphere. So this, you can think of the projection as a way where you transform a 3D point measured in angle into a 2D sheet. The globe transform into a 2D sheet. And there's different ways you can do this transformation. Hence, there will be different projections that's used by different part of the world or by different purpose. For example, if you only want to look at the South or the North Pole, you want to look from the top or the bottom of the Earth. Well, like if you're looking at some particular area, you want the globe to be projected onto the 2D sheets in different ways. So there are different projections. But in a sense, the projected data has the unit of meter rather than angle. So the difference between those two is that when you actually do the geometrical operations or do the computation, for example, when you're trying to calculate the area or the length or the distance, there will be slightly different things that's being done with the different system here. So ST is long let is usually used internally within the SF functions. So the use case of that is if SF is long let gives you a true value, you do certain things, and else if it's false, you do another things to calculate the distance, the area, or length. And then with ST transform, so it allows you to transform from an unprojected map, unprojected globe into a 2D, into a projected map, which is a 2D sphere. And also it allows you to transform between different projections. So allows you to see the globe in different ways. So it's basically allows you to do the transformation on your projection. And here this estimate grids, that's another one that I would use. So basically it would create rectangular or hexagon grids on your polygon, on your area, and then you are able to do some counts within each bin or do something like that. This is something which I find handy. And then definitely there are more SF functions that's available. If you go to the reference page of the package, you actually be able to see there's a lot that's going on here. So here is just like the few ones that I really like, and I think that's worthwhile to share with everyone. So that's the first part of the talk. And then the next part I will talk about is aggregating time series with the tsibble package. So for the 30 stations I have shown you before on the map, we actually have daily information on precipitation, maximum and minimum temperatures. So these are variables that we measured on a daily basis for 2020. So here I plot the maximum temperature for each stations in 2020. And because it's daily data, so all the lines are really wiggly and you have to bear with it. This data is downloaded from the Bureau of Meteorology, and I store it in the long table. So here you have all the IDs for each station, and then date, which shows you what are the dates that's being recorded. It's a daily data, so you basically have 1, 2, 3, 4, 5, keep going on. And then there's the precipitation, maximum temperature, and minimum temperature. We would like to know about the data quality before proceed to any analysis. And the tsibble package has a count gap function that allows you to do this data quality check. But before to use it, you will need to cast your data into a tsibble tsibble object. So what I will do is here on the right, I load the tsibble package, and then you have the data TS, and then you pipe it into tsibble. The 2 arguments you need to supply for kabble to recognize the shape of your data. The first one is called key. So it's the identifier of each individual station. And then the index, which is your column that recognize your date time, your temporal ordering. So the temporal ordering here we have is date. Then we can pipe the created TS tsibble into the count gap. And then the output of it is a separate data summary table. So here you see for each ID, there's the date from to date to, and then it shows you how many missings that's within this range. So for example, in the first line, it reads for station 3057. There's a missing period from the 17th of February to the 18th of February. So that's 2 dates. And then the next line will show you there's another period of missing from the 25th of February to the 1st of March. And that's 6 days of missing. So based on this summary, we can make a plot that's to look at what's the distribution of the missing across time and across stations. So here is the code that I use. I use the geom error bar, so it will shows you like a little bit period, And specifically, what I do here is I ordered ID based on the total number of missings. So I group by the IDs and then calculate the total amount of missings here, and then puts that into factor reorder to do that ordering. And then this is the plot that you would be able to see. So you might be able to see there's some small missing of 1 or 2 days here and there, but overall, the station do not have a long period of missing for the stations. There are a few that you might need to be a little bit cautious. For example, this one here, this station would have almost half a month of missing in July. And also a little bit here, there's quite a bit of missing by the end of March and at the beginning of April, and potentially this one here, during February, there's quite an amount of missing. But overall, because not all our stations are automatic, the way these reads come out is there's someone going to the station every day 9 a.m. to record out all those numbers and then type it into the computer, and then it goes to the BOM. So it's reasonable. There's some human errors. There's some days when these people didn't recognize, and there's some missings. But overall, there's not amount like a 3 months or 5 months period of missing. So these stations are relatively good, and it should be fine just to use it. And at least it's acceptable to me. Sometimes those missings that you see, they are not explicitly stated in your data. So we can inspect, for example, here, we can inspect to see the missing period of 17th and 18th in February, but the data does not speak for itself. And this causes a problem for us because sometimes you can do some calculation and have some unexpected error that you are not even aware of. And on the right, I show you an example where you're trying to calculate a 5-day rolling average, say 19th of February. And if you don't have those NAs registered for you, what you will be using is 4 days that's directly above the 19th of February. And then in here, it will be from the 13th to 16th plus the 19th to do that 5-day summary. But if the missings are properly registered as on the right, you will be using the correct date to do your calculation. So you really want those missings to explicitly standing out to say, hey, I'm missing for you, right? So in a tsibble package, there's the fill gaps function that allows you to have a complete grid on the time so that here I have the single, which shows you a single stations I'm looking at. And then I have the single field, which has the single pipe into the fill gaps. And then the output of that would have the time that's written out for you. And then all the cells here would be just NAs. So that's the temporal part I want to talk about. And then lastly, what I want to talk about is the space and time, to manipulate space and time at the same time with kabble. So one of today's goals is for everyone to be able to make a glyph map similar to this by the end of this session. So you can use the code that I have already provided to you and make some tweaks on that. It should already have the code that allows you to make exactly this map. And then there's ways and rooms where you could tweak around to do some customizations on your own glyph map. So to be able to make this glyph map, there's 2 things we need to first discuss about. We need a data structure, which allows you to do some wrangling in space and time. That's the data manipulation part. And also we need a way where you can draw those small little wiggly lines on the map. That's the visualization part. So for the data wrangling part, I will be using a package called kabble. So a kabble has 2 forms. Right here, And here, these are the nested form where all the temporal data is nested in a list column called TS. And then this form can be used to calculate on the space, to make some calculation on the space. And also you can make some station summary about your temporal data. And another form that Kabble use is to use the long form, which it elaborates the temporal data into the long form, and it will temporarily hide the spatial data for you so that then you can focus on your temporal data. So with the long form, you can make a temporal summary of your data. And so here what I do is I show you the function phase spatial and phase temporal that allows you to switch between these two forms. So this may seem confusing just by the illustration. So what I will do next is to show you the code, which you can actually see the code and then see the output. How does the kabble help you to wrangle your data? So there's different ways you can create your kabble object. So if you happen to have a spatial data sheet and then temporal data sheet, what you can do is you can supply them into a list. So as before, we have already seen the stations SF and also the TS, they are the spatial and temporal data. We can supply them as a list and then specify a few parameters that allows kabble to construct the structure. So the keys and index would be similar to the tsibble object. You would have ID to identify each station and the index to identify each time point. Kabble specifically requires you to have a coords argument to supply the coordinates. In here, it would be the long and lat to specify the longitude and latitude. So this is how a created kabble look like. So from the header here, you would be able to read the 30 stations. It is in a nested form. And actually the nested form is created out of an SF object that's coming from the station's SF. There's the B box that tell you the bounding box. And there's also a line here called temporal that tells you that's the temporal variables that's available that's nested in this TS column. So actually, if you're trying to referring to some temporal variables, you can directly read out of here that's what are the variables that's available for you. So here it should be pretty familiar that we have from IDs to geometries, that's the SF part. And then all the temporal parts, the things within the TS, they are nested here by per station. And to do the subset, so we have the CB object, and then we can do some slicing. So here I just set a random seed and then do some random slice of 20 stations. So here they have all the stations in the 20 that's being selected onto that. So it's being performed on the nested form because it is a spatial operation. And then next we could do some summary on the space. So we have the SF CB space, which is the one after we do the spatial subsetting. We pipe it into phase temporal, which would allow the object to be converted into the long form kabble as you see in the diagram. And then within the long form, we could do a group by, which would, so group by here would create a variable called months, which extract the months from the date and use that as a grouping. And then you'd be able to do a summary of the average maximum temperature of the months for each station. So this is how the object look like in the long form. So now remember, after the subset, we only got 20 stations, and it shows here it's in the long form. And there's a B box that's going on here, shows you the spatial extent. And then this line here, rather than showing the spatial temporal variables, now we have all the spatial variables. So the purpose of that is just make it much easier for you to referring to variables in another form, so that you actually don't have to go back and forth to look at what other variable names. It's already written up for you. And in the output, we have the IDs for each station, the months, which specify which months, and then the summarized Tmax, the average maximum temperature for each stations. Now, so after everything we did before, we should have the longitude and latitude within the nested form, and also the months and Tmax that do the monthly summary in the long form. But if we're trying to plot something within the ggplot, we know that we have to put everything in a single sheet. So here there's a function unfold that allows you to move some of the variable from the nested form into the long form. So here what we do is we move those, the longitude and latitude, into the long form, so they shows up here. And it was not the reason that it's not being shown originally is because you can see here it's basically repeating things of each other. So if you having like an SF object has a geometry and it's a quite large geometry and you have to repeat it at each timestamp, it would be quite costly to store the things if you have daily data, right? So unless you explicitly ask for them to be combined together, it will be separately stored in the spatial sheet and the temporal sheet for you. So this wraps up for the data wrangling in the space and in the time. And the last things before we can making the glyph map is to know about the glyph map transformation here. So a glyph map transformation allows you to put a time series in the space. And the way it do it is through some linear algebra transformation of your axes. So here in one, I have one particular station that in the space, it's in longitude and latitude. And in two here, it has the associated time series that has date on the X, Tmax on the Y axis. So we can use linear algebra to transform the temporal axis into the spatial scale as in 3. So what's different from scale in 3 is that the line is exactly the same, but the coordinates become different. So now it's in the longitude and latitude coordinates. And then because it's in the spatial axis, you can plot that into the map as in D. And within R, you can directly use the geom glyph to do these transformation for you. So it's in the ggplot syntax, and you have to specify 2 pairs of axes, the major axis and the minor axis. And the way it works is that the major axis is the spatial axis. It's, if you look at it in the map, it's the major one that's out there. So in our case, it will be the longitude and latitude. And the minor axis is the small axis that you use to plot this particular time series. So it will be the date and Tmax in our case. So actually from all here, you would have already got all the ingredients that you need to make this glyph map here. And I have the code out there for you. So you will have to create your own kabble from the data that you have. You can do some spatial subsetting and also do some temporal summary to make your data much more smoother. And lastly, you want to make things within the same data sheet. So you use the unfold to do that. And then when you actually make the plot, you want to have a geom SF layer that's a layer underneath that tells you where the shape of Australia. And then you use the geom glyph to actually plot those small wiggly glyph. And then, as we talked about before, the major axes are the longitude and latitude. And then the minor axes are the months and then the Tmax. There's the width and height that allows you to adjust how large you want your little glyph to be. So for example, here you can specify like what's the width on your x-axis and what's the height on your y-axis. And then you can add up some theme and then add up some aesthetics to customize the map as to the way that you want it to be.
May I ask a question?
Yep.
Sorry. So basically, like all those squiggles, there are like little plots, like the little, like you need to specify the axis, which is the size of the little plots.
You want to specify the size, but if we want to be very precise, it's not actually plot. It's not a plot incision. Yeah, it's part of the, it's really just, you can think of it as like a path that's being placed specifically into that point because of given that transformation.
Yeah, and that input represents time.
Yeah.
Rather than
Yeah. So what I want everyone to do is you can go to the repo that's linked within the slides. There should be code already there that allows you to actually create a kabble object from the spatial and temporal data that's already in the repo. And then you could perform an operation on the space in the nested form. That's to have an experience to manipulate the nested form. And then you can switch into the long form to do with face temporal, and then make some summary on the temporal data. So you can make some summary or you can do some subsettings, depends on you how you want to show your data. And then in the end, you want to make a glyph map, use the geom glyph with the aesthetics that the major minor XY axes to make a glyph map. So that's maybe we should do like a your time session so everyone could actually have a try and then see if there's anything you see or any help that you need. What's your experience with that?
To put up the address of the repo.
Yep.
There was a little comment in the chat before from Catherine Lines, and then some of the tsibble word is missing and maybe they still are file. Not sure exactly what was that.
I did some picking in the code that I showed in the index.r file. But if you want to see everything, you can open the index.qmd, which is also in the repo. So that will give you all the code and everything that you see on the slides. And also just a comment here. So there's some developing within the kabble recently. So you do want to install the GitHub the most recent GitHub version. There's things that's going on yesterday. So there's some code that I did. There's some changes that's being made with regards to the latest deployer change. So you want to, if you install from GitHub, before yesterday, you need to install the latest version.
I'm waiting for you to do that little sketching tool on the bottom. Use the little sketching tool.
Oh, this one. I did use that when I was pointing the explicit and non-explicit unknowns. Yeah, this is a really neat functions to use. So we got a question in the chat. So Jacob was asking when would I use a glyph map over an animation on, say, a heat map? So with spatial temporal data, I'm very cautious about using an animation because it's very easy to overload your viewers because there are so many things you need to see, especially if there's facets also coming along and you are viewing so much things and animating things in one go. So there's a lot of things that's moving on different parts that sometimes would be a little bit harder to actually see the things that's actually moving. So if I'm trying to look at some time series within the space, or there's like a certain pattern that's going on the space with those time series, I would try to use a glyph map. Yeah, but also with glyph map, you want to make sure you don't have too many points. There was another example which I put on the tsibble on the kabble repo that I got 600 stations within Australia. That's the full data, and then if we put 600 glyphs on the whole Australian map, there's gonna be yeah, you know what you're gonna see. That's just not wise, right? So what I do is I do some grouping on the stations, and then I turn it into 20 regions, and then I plot the map, and then you will be able to see there's a little bit of trending, or there's a pattern that's going on where in the northern Australia you will be able to see the maximum temperature is pretty flat throughout the year, while like within inland Queensland there's much variations, there's different patterns within different corners of Australia because we're just too large. So with Plotly, you can make plot with Plotly. There's a specific vignettes that I have in the kabble package down website that goes on with how you can make an interactive map with one side being a Plotly map, and on the other side is on one side is a leaflet map, and on the other side is a Plotly time series, which you look at a temperature band, and then you can use the crosstalk to connect the two plot together. So you can make some selection on one plot, and then the other plot would react, and all the other way around. So that's something to check out if you're interested in interactive graphic.
And Just out of curiosity.
Out of curiosity, where like how hard is it to download BOM data, or where do you?
Or
No.
there's quite a bit of script that I use, because what I feel like mainly in the past there's boomerang package, and then for some reason it's it can't use that.
Maybe I can mute myself.
If you want to say.
Oh,
Yeah.
okay. So the download of BOM data is not particularly easy. So in the past is the boomerang package that's available. But what I did was boomerang. Yeah. What I do is I go to the BOM website and then look at their guidelines to do the download. It was not easy in the sense that there's a few dimensions that you have to look at before you make the downloads. For example, like one dimension is the list of stations that you're interested, and then the station, then the parameters you're looking to, and then the time scale that you're looking to. And it's not if you think of that as a cube, then it's not a full cube. There's holes here and there's, and you don't know which station has which variable at which length and at which time scale. So there's a lot of like twiggly around here, and there's yeah, so you have to have a station and then see the parameter, see the time, and then download out things, and then like it amounts to like a script. Yeah. Yeah, sure.
And we probably want to let people in the chat online first, and then we can talk later. Any questions from the audience? Or remember you working on that?
Yep.
Question.
Yeah.
Can it take other geometries other than points? Can it be a polygon or?
So you can have polygons associated with a point. But mainly I think kabble deal with when you have like you have a fixed position station. Yeah.
Like getting the data clean and then in the nice PS sort of data frame.
Yeah, actually what I do is that I have a couple of objects that's already within my package. So I just extract that and extract the spatial component that's stations SF and then yeah, that's reverse engineering.
But I remember because I think some time ago I was working on something like that, you know, in Python, and I never worked with spatial data before. And it was not there. And maybe I don't know.
Yeah, satellite are like yeah, satellite are like raster data. So it's like when you're working on vector, someone's one vector, someone's on another type of spatial temporal. It's like everyone say when working with spatial temporal data. Yeah.
We have a question from Phoebe.
Mm-hmm.
She's going through the index R and in line 62. She's wondering how we define missing data.
In line 62. Oh, yeah, this might I think this part might be missing in the code. Yeah. That's the one you will need. So you first define the missings from the tsibble objects. TS tsibble is the one that we created from TS. And then when you have that, you pipe that into count gaps, and then you get the missings. So the output of it should be a summary table that looks like this. So it's a standalone summary table. Yeah, I think this line is missing from the index.r file. So regarding to Michael's comments in the chat, one thing I would like to include is that often the case, there's something I need is I want to summarize some per station feature or per station numbers from the time series. And then I end up from the time series to come up with another summary table where I have each station's as I write, and there's some numbers are going on. And then there's this particular table, and then and then there's the spatial sheet I had originally have, and then there's the temporal sheet that I have, and that causes quite a bit of headache for me to play around with, struggle around with like 4 or 5 objects at the same time. So one thing you can do that with kabble is that you could actually make per station summary regarding to your time series with a syntax similar to this. So long here is long kabble, and then you can use phase temporal to make it into the nested form. And then on the nested form, what you can actually calculate, say, an average max as the mean of TS max. So that's the T max variable within that TS column. And then you can calculate the mean of that. So that would allow you to directly append this value into your nested form. So if your TS here is a tsibble object, then you can use some of the function from the tidyverts family to calculate some features or potentially even doing some models. And the output would arrange in the nested form, and then it's a per station summary. And this is what I mean by you can what I show here, like with the nested form, you can actually do some per station summary from the temporal side as well. So that's something extra to add. So after your time, there's some further reading that you can look at. I quite like the book Spatial Data Science with Application to R. So it has quite a bit of introduction regarding the SF package and SF cohort. And then the SF, the links for the SF package, tsibble package, and kabble package here. And then alas, it was quarter. It was my first trial to play around with all the quarter stuff and migrating into the quarter sites. It was quite fun. This drama going on, and yeah, there's sketches that's going on and move around things. But yeah. And then you should have all the slides and materials that's to get access to. So yeah, thanks everyone.